Ever wondered how AI models like GPT or AlphaFold achieve human-like reasoning? Today, we're diving deep into the mathematical and algorithmic foundations that make modern AI possible, exploring neural networks, optimization techniques, and the breakthroughs reshaping machine learning. This isn't just theory, it's the science powering everything from self-driving cars to drug discovery. At the core of AI lies a simple yet powerful idea, approximating complex functions through layered computations. Neural networks, inspired by biological neurons, consist of interconnected nodes that process data in hierarchical stages. Each node applies a weighted sum to its inputs, followed by a nonlinear activation function, like ReLU or sigmoid, to introduce complexity. But here's the kicker, these weights aren't hand-coded. They're learned through a process called backpropagation, which uses gradient descent to minimize error. Let's unpack this. Imagine a multi-layer perceptron, MLP, tasked with classifying images. The input layer receives pixel data, hidden layers extract features, edges, textures, shapes, and the output layer produces probabilities. But how do these layers learn? During training, the network computes the loss, a measure of prediction error, then propagates this error backward through the network. By adjusting weights using partial derivatives, calculated via the chain rule, the model gradually improves. This is where computational graphs and automatic differentiation shine, enabling efficient gradient computation even in deep networks. Gradient descent isn't a one-size-fits-all solution. Variants like Atom and RMSProp adapt learning rates dynamically, accelerating convergence. But modern AI pushes further. Transformer architectures replace recurrent networks, using self-attention mechanisms to weigh relationships between input elements. This allows models to process sequences in parallel, a breakthrough for tasks like translation and text generation. Meanwhile, research into neural architecture search, NAS, automates the design of optimal network structures, reducing human bias in model creation. Recent advances in AI are rewriting the rules. Large-scale pretraining, where models learn from vast datasets before fine-tuning on specific tasks, has become standard. Techniques like knowledge distillation compress these giants into smaller, efficient models. Meanwhile, neuromorphic computing mimics brain structures for energy-efficient inference. And let's not forget reinforcement learning, where agents learn through trial and error, achieving superhuman performance in games like Go and chess. AI isn't magic, it's math, algorithms, and relentless experimentation. By understanding these principles, you're not just a consumer of technology, you're part of its future. Dive deeper into papers on attention mechanisms, explore frameworks like PyTorch, and stay tuned as researchers push the boundaries of what's possible. The next breakthrough is waiting for curious minds like yours. Thanks for watching. If you want to explore the code behind these concepts, or dive into specific topics like Bayesian neural networks, hit the subscribe button and let me know in the comments. The journey into AI's inner workings has only just begun.